Hello all! In this video I'm going to be talking about the design and development of this SCARA arm. The arm has got 4 axes of movement, so that's axis A, that's the one I'm calling Z because it moves up and down, and then we have B, which goes this way, and finally we have C, which is here, so we can twist that, and the gripper at the end, which goes whoop, whoop, open and close. A quick overview how some of these axes works. The A axis is down here, so if I open up, let's open up the side of this, and hopefully some of this makes a bit more sense. So you have a motor off driving a pulley via a belt, and that moves the entire axis, and there is this kind of arm, this lever arm, or just an arm, that comes off the side, and that's used to home the A axis. And hopefully you can just see in the corner there, there's a little switch. Maybe if I come around to the other side, this is clearer. So if I open up that side, and as this A axis turns, that arm would engage that limit switch. The next axis is Z. Z's relatively straightforward. In fact, let's go back here, open this up. So inside this pulley, there is a motor as well, and that's the Z motor, and that's attached to the pulley. So as the pulley spins, so does the Z motor, and then as this spins itself, it will drive a lead screw that is attached to a nut, and that moves the entire top assembly up and down. And this is homed via the limit switch on the base pulley, which also moves as the A axis moves. So as the Z axis comes down, it will engage the switch there. One of the design goals of this project was to keep all the weight as central as possible, and that's why we've got these 2 motors over here on this side versus having the motor directly driving the axis on this side. So the B axis, relatively straightforward. So the B axis motor, this one, spins via the timing belt, goes through this pulley, and this pulley is just directly connected to the shoulder, I'm calling it, I guess, which is, excuse me, the forearm. So that would be the forearm, and that would be the shoulder. C rotation occurs from the C motor, which is up here, and as this motor spins, it's going to drive, it's going to transfer its motion via this belt to this pulley. And the pulley has a shaft, and that shaft is just a bolt, but the pulley is printed in such a way that the bolt fits in, the hex head of that bolt will fit into that pulley. So as the pulley spins, so does the bolt, and you can kind of see that in the animation here. So as that pulley spins around, the bolt also spins around, and that's used to transfer the motion from the C motor via the belt, via the pulley, via this shaft, which goes all the way down here and drives the pulley down here. So this has also got the exact same indentation as the top pulley, and inside, or on the other end of the bolt, would be 2 nuts which have the same shape. So they sit inside this pulley. So as the shaft spins, so does the pulley. So that shaft motion gets transferred to this pulley, and via the belt gets transferred to this pulley, which ultimately spins the C axis. And the C axis is homed via a limit switch that exists just on the forearm here. So as it reaches this angle, which is then the limit of where it can rotate, there's a limit switch here that would pick up that motion and would let the controller know that it's reached its maximum position. The B axis is homed via the limit switch over here. So as that rotates and gets to its maximum position, that limit switch picks that up. Speaking of controllers, this arm will be run off a GRBL controller, so a standard Arduino running the GRBL shield with some custom code on it. And the goal is that it does accept standard G-code. The gripper's powered via a servo motor at the moment, and it just has these link arms connected to a linear slide bearing housing with these gripper fingers on there. So as hopefully you can see that motion there. Black may have not been the best color for this, but as the motor spins, those link arms come together and they slide along, and they make the fingers, I guess, slide along the linear rails and close in, and as it spins the other way, the opposite happens. So that rotational motion is essentially converted into linear motion via those link arms and those bearings on those linear slides. That's the overview. Let's make this thing. A quick overview of the code now. We have two main classes: the Axis controller, which is responsible for controlling all the axes. That's built on top of the Axis class, which is responsible for controlling a single axis. In order for the standard G-code to be used, I'm using a library called GCode.h, and I found this library to be very, very useful. I will put a link in the description. The way this works is that each G-code command gets mapped to a function. You create your function declaration up here without the implementation. You then map a G-code command and then the respective callback function for that G-code command. G28 will be mapped to the function G28 home. Write that function, you write an implementation of that function, or the G1 code is over here. You can read the individual values of that G1 command. So you could have G1 Z10, and then you would get the Z value being stored in this variable here. You could have G1, and you can have multiple ones. You can have multiple parameters to that G1 command too. So for example, you have G1 A30 and B20, then both of these, the A variable and the B variable, will both get their values off the command's value buffer. The B axis and the C axis has to be kept in sync, because as B moves, C also moves, so you have to offset C's movement by B's value. Sounds way more complicated than what it is. And then you can actually call the move function, accepts the degrees for the A, B and C axis, and the millimeters for the Z, and then it performs a synchronized move via the sync drive library, which is the low-level stepper controller library. The limit switches are done off interrupts. Every time one of those limit switches are hit, we just call a function that's implemented in the Axis controller that will perform the action that it needs to do for each of the limit switch hits. At the moment, it's only transitioning the homing state. So you have an initial home at a relatively fast speed. You retract a few millimeters away from that hit, and then you slowly back into that limit switch again, and that should get you to the home. And this code implements those state transitions, but I will put a clip of the homing, which hopefully makes what this is trying to do a lot clearer. The init gripper creates the stepper motor. No, the init gripper creates the servo motor that you need to run the servo code. Home axis will essentially call each of the individual axes home sequence and then move into a default position, which is done here. I need to get rid of these magic numbers at some point, but hopefully it should make relative sense in terms of what it's trying to do. And then loop simply processes the G-code commands, and then it updates the servo. The config was working out what is 1 degree for each of these axes. So apart from Z, which is done in millimeters, so that was relatively straightforward. It was just based off the pitch of the lead screw. But to work out a degree for an axis is a factor of the ratio of the motor pulley to the pulley that it's driving, its micro steps, and its steps per degree, so the specification of that motor. But once these ratios were worked out, this formula could be calculated. So that's how many steps it takes to move for a degree, given the different ratios of the pulleys and the micro steps of the motor that it's being run on. It was time to solve real-world practical problems, such as stray electrical tape being outside its Tupperware box. Can it do it? Turns out it could. And with that, I would like to thank you very much for watching, and I'll see you next time. Cheers.